In this video, let's talk about the solution of this system of differential equations. X prime, the vector x prime is equal to this matrix at -8, 2, 6, -7 times the vector x. We're going to determine if the origin is a saddle point, source node, or sink node. We'll also determine if the origin is asymptotically stable or unstable, and draw sample solutions. After figuring out the general solution, we will then use this initial condition to solve an initial value problem. To get started, we note that this is a matrix A, and so I need to find the eigenvalues and eigenvectors of this matrix. And so I will use my shortcut method of doing so. First, I figure out the trace of the matrix. I get that by adding the diagonal elements, -8 plus -7, so -15. And I also will figure out the determinant of this matrix. The determinant of the matrix will be -8 times -7 minus 6 times 2. And so that works out to be 44. And so the eigenvalues I will find by solving r squared minus -15 times r plus 44 is equal to 0. And so I get r squared plus 15r plus 44 equals 0. If necessary, I use the quadratic formula, but this one actually factors r plus 11, r plus 4 equals 0. And so I get my two eigenvalues to be -11 and -4. From this right away, I can conclude a couple of things. The origin, I will see, is going to be a sink node. Both eigenvalues are negative. And because it's a sink node, that means that the origin is asymptotically stable. So all trajectories are going to point toward the origin. To find the general solution, we now need to find the eigenvectors associated with these two things. So I get the eigenvector for r is equal to -11. So my shortcut formula is b r minus a. There is a more general method that you probably saw in linear algebra, but because this is a 2 by 2, I'll use my shortcut method. The b is the upper right-hand corner of this matrix 2. My r is -11 in this example. And the A is the entry in the upper left, so I get -8. And so I will get 2, -3 as an eigenvector for this direction. And any constant multiple will also work. There's no simplification necessary here. That's pretty simple as it is. To get the other eigenvector for -4, I once again will plug in into my shortcut formula, b r minus a. The b will still be equal to 2. My r has changed to -4 minus -8. And so I will get 2, 4. Now, once again, any constant multiple of this will work. And so let me take the somewhat simpler constant multiple of 1, 2. And so from this work, I conclude that my general solution is going to be x of t equals c1 e to the minus 11t times 2 -3 plus c2 e to the minus 4t times 1, 2. And so that'll be the general solution. Now, to sketch the solutions of this, we will draw the coordinate plane as usual. Okay, so we have one eigenvector at 1, 2, so that'll be in about like this, and that'll be pointing inward. That's the eigenvector corresponding to r equals -4. And then the other eigenvector is going to be for 2, -3. So 2 down, 3 over. So it'll be something like this. Or, sorry, 2 over, 3 down. I drew it incorrectly. So something like this. And that'll be the direction for r equals -11. Now, for all other eigenvectors, they're going to be pointing in toward the origin, just like all of these. When t is large, the smaller eigenvector in absolute value determines the behavior close to the origin, and it'll be parallel to the bigger eigenvalue in absolute value. And so close to the origin, it'll be coming in along like this. And then in the other direction, it'll be like this. So parallel to this eigenvector, and then turning, and then going alongside this eigenvector. And so another one might be like this, where it starts like this, then turns into the origin. For something out here, it would come along this direction, and then turn into the origin. Likewise out here, it'd be parallel to the far side, and then turn into the origin. And then out here, again, parallel to this eigenvector, and then turn in parallel to the, and then turn along this eigenvector to the origin. So those are some sample trajectories. Now we solve the solution of the particular solution when we have, or solve the initial value problem. When I have t is equal to 0, I would have c1 times 2, negative 3 plus c2 times 1, 2 is supposed to be equal to the initial value of negative 4, 0. Now, there are several ways that this can be solved. The technique that I will use an augmented matrix. So this can be thought of as 2, 1, negative 3, 2 times negative 4, 0 like this. And the reason that I can do this is because this equation can be thought of as 2, 1, negative 3, 2 times C1, C2 is equal to negative 4, 0. And then this has the familiar form of an augmented matrix that we've seen from algebra, from linear algebra. Okay, and so top equation will divide by 2. Then I'll take this new equation, multiply it by 3, and add to the bottom equation. So multiply that by 3, get 3 halves plus 2, 7 halves. Multiply that by 3, negative 6 plus 0, get negative 6. And so from the bottom equation, I see that C2 is equal to, or 7 halves C2 is equal to negative 6. So that C2 is equal to negative 12 sevenths. Coming to the top equation, I see C1 plus a half times negative 12 sevenths is equal to negative 2. And from that, I conclude that C1 is equal to negative 8 sevenths. And so therefore, my solution of the initial value problem, where I have this as my value at time 0, is going to be, well, again, I come back up here to my equation here, and I use the C1 and C2 that I just computed, negative 8 sevenths, e to the minus 11t times 2, negative 3, minus 12 sevenths, e to the minus 4t times 1, 2. And so that will be the solution of that initial value problem.